the Bible says that he made the stars also. The Creator God made the stars. But what else do we really know about them? Jeffrey Burbidge is an eminent astrophysicist, well known in both the United States and Europe, and this is what he had to say. This quote really summarises what I'm going to talk to you about today. Underlying all of the topics in the extragalactic universe and the physics of active galaxies are two basic beliefs. Note, underline, beliefs, which are widely held. Number one, the cosmological evidence strongly suggests that the hot Big Bang model is generally correct. That's point one. And point two, which is much more relevant to my talk today, that redshifts of all objects outside of our galaxy, apart from some small velocity shifts, are due to local motions, are cosmological in origin. In other words, all the extragalactic redshifts are due to the expansion of the universe. He says, in my view, the general acceptance of these ideas and the subsequent edifices of the models that have been erected around these ideas is a fundamental mistake. The direction that research will take in the 21st century, however, may well lead to a compounding of that mistake, and I predict no immediate return to reality. Now, this guy is an expert in this field, and this is his opinion. So I want to show you a little bit more about this issue of redshifts. Everyone may recognise this. It's the Hubble Space Telescope. It is in orbit above the Earth, outside the atmosphere, where it has a very clear view of the sky, or the stars, and the cosmos. It has a much better view of the galaxies than any of the large Earth-based telescopes, like the big 8-metre ones in Hawaii. And this telescope has revolutionised what we know about the universe. It has taken many, many very surprising pictures that have changed the way astronomers think. Also, in recent years, there have been many new types of telescopes put into orbit, some that can see in X-rays, some in gamma rays, some that see in infrared light, and some that see in ultraviolet light, which we can't normally see with our eyes. This is a picture also that's been very popular, made very popular over the years. It's called the Hubble Deep Field, and it's a photograph taken with the Hubble Space Telescope over a period of about 10 days, 153-hour exposure of a piece of the sky, for all purposes looked black. There were very few stars in that area. The area is the size of what the moon looks like to us from Earth. So it's quite a large piece of the sky. Now, in amongst this picture, you'll see many galaxies, and more than 50% of those galaxies look just like the galaxies that we see around our galaxy, in our galactic neighbourhood, if you like. And the rest of them are peculiar, but we'll talk a bit more about that later. In order to get an idea about the universe, the first thing I need to explain, and you need to get an idea of, is the distances in the universe, the size of the universe. So let's have a look at a few distance scales. The first one, the distance to our sun, from Earth to the sun, is 150 million kilometres, approximately. To get an idea of that, if you were driving your car there at 100 kilometres an hour or 60 mile an hour, it would take you 170 years to get to the sun if you took no toilet or bathroom stops, didn't have to repair the car or anything like that. It's quite a distance. Who knows what a light year is? Put your hand up if you think it's time, a measure of time. Put your hand up if you think it's a measure of distance. Wow. Put your hand up if you don't know. Oh, good, there's a few honest people here. But definitely you're an educated lot. Yes, it's distance, a measure of distance. The speed of light is about 300,000 kilometres per second, and it's the distance that a pulse of light will travel in 1 year, which is quite a long distance. About 10 million kilometres, or 6 million miles. It's around 63,000 times the distance to the sun. Besides our sun, the closest star Alpha Centauri, is 4 of those light years away, approximately. Now I want you to imagine, out to the distance of Alpha Centauri, place a sphere centred on the Sun, and the edge of the sphere is out at that distance. It's like an empty ball, if you like. And then imagine that you take all the stars in the universe and you pack them into that ball. Well, you'll be very surprised to know that 100 billion galaxies of 100 billion stars, which is that number there, 10 to the 22, or a 1 with 22 zeros after it, all those stars will fit into that ball without touching. This gives you some feeling of how large the universe is. And that's only out to our nearest neighbour star. It's very empty. When we look up into the night sky, away from Sydney of course, and provided there's no moon, you'll have an opportunity to see something like this. And we're looking through our galaxy, we're looking towards the central galactic bulge, which is where most of the stars are concentrated, and we see a lot of gas and dust in that direction. If you look up like directly above that, at 90 degrees, you'll see very few stars. Of course, this is called our Milky Way galaxy. To get some idea of the size of our galaxy, I hope you can see this. If you were in a spaceship and you flew up out of the galaxy, above the plane of the galaxy, and looked down, you would see it like that top picture, a large spiral structure with many arms. The size of that structure is around 100,000 light years across. If you then flew your spacecraft the other direction, out on the edge, you would see it looking like this. Now, the next big galaxy next to ours is often called Andromeda, or M31 for the astronomers. It's approximately 2.5 million light years away. That's around 25 times the diameter of our galaxy. And it's roughly the same size as our galaxy. Now, what do astronomers really measure? Astronomers are scientists who work with light. They measure light, they have telescopes. The light can take many forms though. It can be in, as I mentioned before, X-rays, gamma rays, infrared, a whole range. But they measure basically 2 things, and one is the brightness of stars or galaxies. We call it magnitude. From this magnitude, they determine distance. And the second thing they measure is redshift. So really they only measure 2 things, distance and redshift. Now I've explained a little bit about distance, so now I'll explain to you what redshift is. When you see a prism like this, it splits light, like a rainbow. It scatters light into different colours or different frequencies. Now astronomers use this type of device to split light from stars and galaxies. The gases in stars, or the elements that are in the gases, will cause the light to scatter into this spectrum of various colours, but it will contain many lines. These lines here, red lines, blue lines, right through the spectrum. This one here is typical of nitrogen gas. And there are many, many different elements in stars, in their atmospheres, and from this type of analysis we can determine what those elements are. Now, if an astronomer sees a spectrum like this, and the lines compared to a laboratory sample are all shifted towards the blue end of the spectrum, then they would call that blue shift. If the lines are all shifted towards the red end of the spectrum, they would call that red shift. So astronomers are not measuring anything but lines on a photographic plate or lines on a digital image taken from their modern digital CCD cameras. But what is the cause of redshift? I'd like to investigate this, and I'm going to illustrate it with a little picture here. This one is for the Doppler effect. Everyone is familiar with the effect of a train rushing by, and if it's coming towards you, you hear the sound, the pitch of the sound shifted up to a higher frequency. And if the train is moving away from you, the pitch of the sound is reduced to a lower frequency. This is for sound, but the Doppler effect occurs exactly the same with light. If the object is coming toward us, it would be a blue shift, and if the object is moving away from us, it would give us a red shift. So if an astronomer sees a red shift in starlight in a galaxy, he immediately thinks that the galaxy is moving away from the Earth. Would you trust this guy? Really, all you need to know about relativity is that speed and gravity affect time and lengths. And the most significant aspect of that in this discussion is time. My work involves very precise clocks. I work at a research lab in the University of Western Australia, and it involves clocks similar to this one. This is an atomic fountain clock. It's the latest generation of atomic clocks, and it cools a bunch of cold cesium atoms here and sends them up. It's called a fountain clock because it's like a fountain, and comes down and they interrogate the atoms here. But in order for this clock to work at an optimal performance, at what they call a quantum limited performance, it needs one of the clocks that I build. And my type of clock is a classical clock, and it's made with a single crystal of pure man-made sapphire. That's about 5 centimetres in diameter, and it's placed in a cryostat and cooled to around about 6 Kelvin, which is roughly 270 degrees below zero in centigrade scale. And we build an oscillator based on this crystal, which has a quality that will allow us to build very, very precise clock. It's something like the arms of a grandfather clock that are maybe miles long. Our clock actually would gain or lose a second in around about 100 million years. So it's probably a lot more precise than anything you have on your hand, on your arm. Now, our clock is used as a flywheel to drive this atomic clock, something like the flywheel in a car. Because the car only fires its piston every now and again, a flywheel keeps the timing. So ours is essentially the same. Ours has interrogates atoms 10 billion times a second, whereas the atomic clock only does it once per second. The atomic clock with ours will achieve the best accuracy of any timepiece in the universe. It is accurate to 100 trillionths of a second. So you can do a lot of very interesting measurements with that. You can measure the differential flow of time. If you place one of these clocks on the top of a mountain and one down in the valley, on the side of the mountain, you can measure the flow of time in these two locations and compare the two, and believe it or not, time flows more quickly on top of the mountain than it does in the valley. When I told my wife about this, she says, "Oh, does that mean the gravity bends the arms of the clock?" Well, in this case, there are no arms. It's the fact that gravity affects time. The stronger the gravity, the slower time passes. This effect can be interpreted as a redshift effect, and that's why I'm telling you about it. GPS satellites are very common today. Anyone here have a GPS receiver? With this, you can tell where you are on the surface of the Earth. GPS is a collection, or 25, they call it a constellation. It's a man-made constellation of 25 low Earth orbit satellites, about 200 kilometres up, and your GPS receiver will determine its position on Earth by doing some sort of triangulation with the signals from those GPS satellites. And they all carry atomic clocks. However, what's interesting is that atomic clock on the satellite beats or ticks a fraction faster than the atomic clock on the ground. And so when the signal is received on the Earth, corrections have to be made. And it arrives roughly 42 picoseconds too soon, because the clock on the satellite is ticking a little bit faster than the clock on Earth. The exactly same type of clock, I mean. Picosecond, by the way, is a trillionth of a second. It's not very much, but if you add it up over a year, it adds up to a few microseconds. So it has to be corrected for. This atomic clock they use is an earlier version of a cesium beam clock. if they used our new super-duper clock, you would be able to improve your accuracy. I think currently you have a precision of about 100 metres, something like that. If you used our clock, you could know your position on the surface of the Earth to 1 centimetre. And you could even build bridges and buildings using GPS with such a system. This effect, this gravitational effect, causes redshifting of the light from our sun. The mass of our sun is pretty massive, 10 to the 30 kilograms, that's 1 with 30 zeros in kilograms, and it's quite large, around 1,400,000 kilometres in diameter. From this we can calculate the redshift. It's pretty small, 0.00004. That's pretty small redshift. It's a little bit too small to measure. But redshift for other stars is routinely measured. So that's two forms of redshift, Doppler and gravitational. And the other form is called cosmological, or due to the expansion of space. So we call it a space expansion or cosmological redshift. And the way this works is, if you can imagine this nebula here started out with blue light, and the light left the nebula and travels on through the universe towards the Earth. And when the light is received at the Earth, the wavelengths are stretched out and it appears reddened. And the reason is, between the time the beam of light left the nebula and the time it arrived on Earth, the universe expanded. And this causes a stretching of the wavelengths. This effect causes a redshift that's indistinguishable, in fact, from the Doppler effect. You know, this is the one due to the velocity. In fact, astronomers always refer to redshift as velocity because they can't distinguish between the two effects. In 1920, there was a guy called Vesta Slipher, and he noticed that the light from galaxies was redshifted. He looked in their spectra and he see the lines were shifted towards the red. And later Edwin Hubble, actually for many decades, catalogued and measured the redshift of galaxies. And he noticed an interesting effect. And I've tried to illustrate it by these red lines here in the image here, in the slide, that the greater the distance the galaxy was, the greater the redshift, which to an astronomer means something like it's moving away much faster. But more importantly, this effect was seen right across the sky in all directions. And this effect has become known as the Hubble law, which says the greater the distance to the galaxy, the greater the redshift. The constant of proportionality has become called the Hubble constant or the Hubble parameter, which I'm sure many of you here have heard of. This is really what Hubble saw. He was sitting on Earth and he saw the galaxies all moving away from the Earth. He came to realise from this that he was located at the centre of the universe, because in every direction he looked, this law was applied. The greater the distance, the greater the redshift. And he realised he must be at the centre of the universe. But the Big Bang people would have us believe that we are located on a galaxy, or in a galaxy, on a planet, of no special importance, of no significance in the universe. And Hubble was obviously very tormented by this idea, and he wrote in his 1937 book, such a condition would imply we occupy a unique position in the universe. But he says it's intolerable. So his bias, his preconceived notions, forced him to conclude that there must be another solution, that the obvious could not be true. And he says it represents a discrepancy with the theory, because the theory postulates homogeneity, which means that the universe is the same everywhere. And so his bias overrides even what his observations were telling him. So astronomers and cosmologists have tried to reconcile this, and I'll explain that in a minute. But just so you get a bit of a better understanding of what Hubble was really looking at, it's illustrated by this slide. Really, galaxies move in clusters, and within a cluster they have local motions. They're moving in different directions. Occasionally you'll find a galaxy that's actually moving toward us, and those few galaxies have blue shifts. So nearly all clusters of galaxies, and nearly all galaxies in fact, have red shifts, but a few have blue shifts. And one of them is Andromeda, the M31, moving about 100 kilometres per second toward us. But don't worry, it's a long way away. So astronomers interpret that as expansion of the galaxies into the universe, where the cosmologists interpret it as the expansion of the universe. Now, I have to explain a little bit about Big Bang, which you've seen this quote before. The universe burst into something from absolutely nothing, zero, nada, and as it got bigger, it became filled with even more stuff that came from absolutely nowhere. This is from Alan Guth, who is the author of the inflation model, the hot Big Bang inflation model. And he said just after the Big Bang, in fact, 1,000 millionths of a second after the Big Bang, that the universe expanded by a factor of 1,000,000,000,000,000,000,000 times in only 1,000 millionths of a second. They've really got a very strong faith, these guys. So just reviewing here, what cosmologists really believe is that the galaxies are fixed in the space and the space itself expands. Something like this. They propose this model because they have to get around this issue of us being at the centre of the universe. So instead they suppose that the universe can have a centre anywhere or everywhere. There are two types of Big Bang models. There are many models, but there's two types of classes of models. And one type, both types have no edge, unbounded, no edge, but one type is like something like the space we think we live in now. It's flat space, not curved, and it goes on forever and ever and ever and ever. It's infinite in expanse. And in such a universe, you could move anywhere and you would see approximately the same picture, like the centre is everywhere. The second type of model that has been very popular over the years is where the universe is finite in size, unbounded, but finite. So if you were in a spaceship and you could live long enough, you could fly off in one direction, and eventually, because the space is curved like a ball, you would come back to the same place. And in that model also, you could move to any galaxy in that model and look out at the stars, and it would appear like you're at the centre of the universe. So this is the Big Bang cosmologist solution to this problem that Hubble had. And it goes something like this. If you imagine this girl blowing this balloon up, and instead of those little galaxies drawn on the balloon, a more correct representation would be to imagine them as like buttons glued on. So when she blows up the balloon, the buttons don't get any bigger. They just expand with the expansion. It's like a two-dimensional representation. It's not an explosion of matter into space, as we would understand it. It's the expansion of the space itself. And the surface of a balloon is something like our globe. It's two-dimensional. And what you have to then imagine that you add an extra dimension, and it's curved into a fourth dimension. Now, it's pretty hard to imagine things in 3 dimensions, let alone in 4. Humans just can't do that. In fact, they call that, I like this word, they call it a 5D brain world, 5-dimensional brain world, B-R-A-N-E. One might think they need to get a brain sometimes. So let's review. What do we really know? One is astronomers measure distance and redshift. 2, for very distant galaxies, the Hubble law is used. So really they only measure redshift, and from the redshift they determine distance. So for most of the distant galaxies, in fact most of the real usable part of the universe for cosmology and Big Bang cosmology, they need the very distant galaxies. And so really they're only measuring redshift, not distance. Astronomers call redshift a recession speed, and it's something like the Doppler effect. Cosmologists interpret it in terms of the galaxies being stationary in the space, and the space is expanding and getting larger, and therefore the galaxies appear to be rushing away from us, the observer. So there are three possible causes of redshift. Remember, they only measure redshift. After that, it's an interpretation on what that redshift really means. It could be due to velocity or Doppler, gravitational, or cosmological expansion, the expansion of space. Now, this is a very simplistic view of what the Big Bang model says about the formation of the universe and galaxies in particular. First, there was the Big Bang, and it exploded, and there was a lot of radiation, which was a hot ball, fireball, expanding out. And then there was a separation of matter into antimatter, and that's got a lot of problems, but we won't go into that here. And then from the matter, not the antimatter, but the matter was the formation of galaxies and stars, which according to Stephen Hawking's latest book, he still doesn't know how they were formed. Mind you, if you take all the stars and galaxies out of the universe, you don't really have much left to work with. And from the formation of galaxies, they were split into two main types of galaxies. One is elliptical type galaxies, which are like these balls of fuzz. They have no spiral structure to them. They're not really rotating. And the other type are spiral type galaxies, which have these beautiful spiral structured arms, like the galaxy that we live in. Initially, galaxies tend to start out as being very active, disturbed. They're emitting a lot of gamma rays, X-rays, very violent type of places. And after billions of years, they're supposed to settle down into being quiet, docile, inactive galaxies like the one we live in. But is this really the case? The picture here is of the astronomer Alton Arp. For 29 years, he worked as an astronomer at Palomar and Wilson observatories, and he has taken many slides, many pictures of very strange and peculiar galaxies. Alton Arp is not a crackpot. He's an eminent scientist, and he realised that that picture I just described to you before is not correct, that there are many galaxies that don't fit the picture. And because of his rather controversial work, he was banned from any more telescope time in the large American telescopes, and he was more or less banished to Germany. Now he works at the Max Planck Institute. But he has come up with many very interesting observations that I want to explain to you now. Here is a galaxy, and it has a companion galaxy next to it. This galaxy here, the large central one, has a redshift of around 8,700 kilometres per second. Remember, I told you astronomers always write redshift down as a velocity, so don't be concerned about that. This one here, which is next to it, has a redshift of 17,000 kilometres per second. According to the Hubble law, which says the greater the distance, the greater the redshift, it would mean that this galaxy would be close and this galaxy should be very far in the background. And this is what the Big Bang community would say, that it's an accidental coincidence that this galaxy just lies so close to the other one in the line of sight. They are not actually physically close to each other. Okay, that would be fair enough, but there's a problem. Alton Arp has found, and it's hard to see here, but there are bridges of material that actually physically connect the two galaxies. They are physically connected to each other with gases that emit X-rays and other materials, stars and dust and so on. So this brings into doubt the whole Hubble law regime upon which Big Bang cosmology hangs. This is a picture of Markian 205, that's the one up in the top right-hand corner. It's a quasar-like object, and I'm going to explain to you in a minute what quasars are. And this one here is a galaxy which is a disrupted spiral, very active, meaning it's emitting a lot of high-energy radiation like X-rays and gamma rays. This one here, the quasar-like object, has a redshift of 0.46 and one of 0.6, which is nearly half the speed of light. When I write it like this, it means it's a fraction of the speed of light. So it's moving away, according to Hubble law, very quickly. And this one has a very small redshift, which is only 7% the speed of light. So according to Hubble law again, this one should be very close, and this one should be right out on the edge of the visible universe and should have no connection between these two objects. Several years ago, ARP published a paper showing that there was a bridge connecting these two objects, a bridge of gas and dust, X-ray emitting material. So the Hubble telescope was placed only a year or two back. They looked at this object and they published these images to disprove ARP's paper that there was no connection. Now, I hope you can see this, but I've reversed the image and changed the contrast. The image itself actually shows a physical connection between the two objects. And this is the image that the Big Bang community used to disprove ARP's hypothesis that they were physically connected. Yet they've actually even proved it further. This image here is taken in X-rays. So instead of using light to form the photograph, they've used X-rays. The colours are false, just so that you can see it. They're false colour image. And this object is Markian 205, which was that very small object in the top right-hand corner of the previous slide. It actually has 3 quasars in it. And there's one that's 1.26, which is very, very close to the speed of light, if you believe the Doppler interpretation of redshift. We only measure the redshift of the lines. We don't actually measure velocities, and we're not really measuring distance. So what ARP has shown, that these objects are all physically connected to each other. You can see that X-ray emitting material, these red lines, envelop these other objects. It's all one connected object, and these are disturbed X-ray emitting galaxies of some kind. So if ARP is correct, he indicates, at least for a class of objects like these very active objects called quasars, that the Hubble law doesn't work. And this is completely a complete radical view in terms of the standard Big Bang model. So what is a quasar? Does anyone know? Can anyone tell me what a quasar is? No. Well, I'll tell you something. No one else knows either. There's no astronomer that knows what a quasar is. Yet there's hundreds of thousands, maybe millions and millions of them in our visible universe. Just to describe a little about what they are often called QSOs, or quasi-stellar object. The word quasar comes from quasi-stellar radio source. Originally they were first seen only in radio waves with the first radio telescopes. They are very star-like. If you look at them, they don't look like a galaxy. They look like a star. Very bright and very compact, like a pinpoint of light. And they have a spectrum that's quite different from a star. Now, I don't know if you know this, but our sun emits radiation mostly in infrared and visible light. There's a very strong peak in the spectrum in that range, and that's so life on Earth can exist. The infrared is for heating, for warmth, and the visible light is so we can see, photosynthesis and so on. However, a quasar emits radiation right across the frequency band. Gamma rays, X-rays, radio waves, optical light, visible light, infrared, ultraviolet, everything. and it's flat. It's the same amount of radiation across all the different regions of the spectrum. They have very bright emission lines, like I showed you those lines in the nitrogen gas, and they all have very large redshifts. The secular astronomer, cosmologist, believes that they are supermassive black holes with maybe like a million or 100 million times the mass of our sun, all packed into a black hole with a very large accretion disk, a disk of matter circling around it that causes it to radiate a lot of light and is very bright. This is an artist's picture of a black hole with a star nearby getting sucked into that black hole. So this is only a black hole with a mass of like our sun. So they're imagining that quasars have millions of times the size of our sun, the mass, the size of our sun. And the idea is they have a accretion disk around the black hole, and it radiates a lot of material like this here, and also a lot of light. This is an object in the galaxy NGC 4438 that astronomers suspect is a real black hole. This is a picture taken with the Hubble Space Telescope, and it seems to have a disk around it, and it seems to be radiating matter out of its central spin axis. However, this object is around 10 million times too dim to be a quasar. It's much, much, much too dim. So even the few suspected black holes don't appear to look like quasars. This is one of the first quasars ever observed. It looks like a star, very, very bright. And notice there's some material being ejected out of it. That's just there. So it's interesting that if these quasars are out on the edge of the universe, you shouldn't be able to see any stars around them. And this photograph here is the same quasar where a disk was placed with the telescope. They placed a disk over the bright central image, and they could see fuzz around the quasar. It appears that you can see the stars that are in some sort of a galaxy around this quasar image. That also is a problem for Big Bang cosmology, because if it's out on the edge of the universe, you shouldn't be able to see anything. But according to Arp's interpretation, he suggests that quasars are a lot closer. They're not so distant, and that their redshift is not due to the Hubble law, not due to the expansion of the universe. This is a picture taken in X-rays and in light, visible light. The colour part of the picture is a galaxy taken with the visible light, and the lines are X-ray images. So it shows the intensity of the objects. And there's a quasar here and a quasar here. These are X-ray quasars because they're very strongly emitting X-rays. In optical, if you look in visible light, you'll see them as a blue stellar object. That's why it's called a BSO. This type of galaxy is a very active galaxy. They're known as Cepheid galaxies, and they are very disturbed and radiate enormous amounts of very deadly gamma and X-rays. What's interesting, though, is Arp has found there are many examples where you find two quasars or more paired across a galaxy. That's across what we call the minor axis. This is the spin axis, and that one there is the major axis. That's like the flat plane of the galaxy. Here's another example. This in the centre is a Cepheid galaxy with a very low redshift, and there are two quasar-like objects with large redshifts, and they seem to be aligned across the minor axis of the galaxy. There are many, many examples of this, and Arp has published many on his webpage. In this one here, this is called ultra-luminous infrared galaxy, or galaxies. This one is called ARP 220, and there's a number of galaxies here. There's a collection here. This galaxy here is a very low redshift, and these ones here also very low redshift, compared to these two X-ray quasars, which have very, very large redshift. So if you believe the Hubble law and the Big Bang interpretation, these quasars should be billions of light years away from these galaxies here. But they seem to be connected by all this hydrogen gas which is emitting X-rays. And it also appears like this object was ejected from this galaxy or group of galaxies, and possibly even this one ejected this way from this galaxy. So this is now a schematic. It's a summary of ARP's work over many, many years, and there are many, many examples of this. He has found that if you look at a galaxy edge on, that within about 20 degrees of this minor axis, he finds pairs of quasars or quasi-stellar objects. In fact, in many cases, there's multiple numbers of them. So he is suggesting that the quasars are physically associated with those galaxies, and in fact, that they have been ejected from the galactic cores, which is a very different creation scenario from what the Big Bang people believed, because they believe all galaxies in the universe were created about only 1 billion years after the Big Bang. So what's the big deal? Why are Big Bang cosmologists so adamant about the distance to quasars? If redshifts for quasars are not due to expansion of the cosmos, then they must have a different cause, right? Maybe it's something intrinsic, but it's not due to the expansion of the universe. So that would change our view of the universe as to where these objects, these quasars, where they are located. So that means the assumed distances to the vast majority of galaxies, active galaxies and quasars in the universe is wrong. This means the Big Bang model comes crashing down. The reason it discredits the Big Bang is summarised in these 2 points. The key assumptions of the Big Bang are, 1, that the origin of all matter was in the hot Big Bang. All matter and therefore all galaxies. And 2, that many distances are determined from quasar redshifts, particularly all the very distant objects. The main thrust of ARP's observations are, if quasar redshifts are not related to the Hubble law, not related to distance, and therefore the Hubble law, then the Hubble law doesn't work, for quasars anyway. And 2, that matter is created from the centre of active galaxies, which are also quasars. In fact, ARP's view is that there's a whole range of types of active galaxies, from Cepheid galaxies all the way through to very active quasars. If this view was not of importance, then Joseph Silk wouldn't have written this in his book entitled Big Bang. And he says, in regard to ARP's interpretation, that this ejection of matter from the cores or the centres of galaxies, he says, only by disputing the interpretation of quasar redshifts as a cosmological distance indicator can this conclusion be avoided. He knows it's so important that they cannot allow this interpretation that ARP is promoting, because otherwise the whole of the Big Bang cosmology will collapse like a house of cards. This is a schematic of what ARP suggests is actually happening. You have a parent galaxy, and from either side of a parent galaxy you have ejection of a quasar pair. After time, the quasar is moving away from the parent galaxy, and its redshift, we call Z here, the redshift, drops down, seems to drop down. And slowly the object changes into various type of active galaxies or blue stellar objects, or there's another kind called a BLAC object, and eventually becomes a normal galaxy. And the other way I've tried to illustrate other aspects of this, where it may become a very active X-ray quasi-stellar object or this BLAC object, and sometimes they split up into multiple galaxy clusters. So this is the interpretation, and this is one of the beautiful galaxy clusters called Hubble 2218 that ARP suggests originated from this ejection of matter process, taken by the Hubble Space Telescope, of course. So my view is this, that we're looking at a creation process, something like a fireworks display where you see the little embers explode, and from the centres of burning embers you find more material coming out, and then they explode, and so on, in some sort of grand hierarchy. Do you get it? So what I'm telling you is, I suggest that ARP is correct. But for a creationist, what is actually happening is we are seeing the creation of galaxies at the very creation itself on day 4. Because we can look out into the cosmos, we are essentially looking back in time a little bit. And we are seeing the creative process of God, who created the universe through a grand hierarchy, where he created galaxy from galaxy, all on day 4 of creation week. So we are seeing God's creative process right now, not after the fact, but actually as it's happening. It happened 6,000 years ago on Earth clocks, not millions and billions of years ago. If we look in the northern sky around the Fornax galaxy, and we take ARP's interpretation of distances, we see it forms a giant S shape. Not only did God create his universe with galaxies with spiral structure, he formed he's formed the galaxies into a supermassive spiral structure, a supercluster of clusters, all in a giant spiral structure. And that's in the northern hemisphere around the Fornax galaxy. In the southern hemisphere, there is another one around the Virgo cluster. This is what the Big Bang universe would look like, with the Big Bang assumptions and interpretations. The yellow are quasars and the green are galaxies. Now let's look at what the universe would look like with the ARP model applied. However, the size there should be contracted down by about 100 times. I've allowed it to be large so you can see the difference. So the universe looks a lot emptier. It's just that we can't see beyond there. There are very few galaxies we can see beyond our local superclusters, the Virgo and Fornax superclusters. To top it off, the redshifts of these quasars ejected from these galaxies seems to fall into certain special numbers. When they've looked at collections of quasar redshifts, like 7,000 of them, they found they all fell very close to these special redshift numbers. Nobody has been able to explain that as yet. I have a view as to what quasars are. I believe that they may be white holes. Everyone's heard of a black hole? Well, a white hole is a black hole running backwards in time, time reversed. Matter is pouring out of the white hole and it's very bright. In fact, observations indicate that matter is only seen to be leaving. It is never seen to be falling in. If it was a black hole, we would see matter falling in. The cause of the redshift, my guess, is its gravitational redshift. And these are supermassive white holes that have very, very high gravitational redshift. The effect of the redshift dropping down to different amounts is like peeling an onion. You take a layer of matter off and the redshift drops down, take another one and drops down even further. So my conclusion is, God made the stars and we're seeing them, and the Big Bang cannot explain it.